In last chapter, we have seen how to write differential equations for electrical and mechanical or electromechanical systems. After that, we have seen how to represent the system in block diagram, like DC servo motor and AC servo motors, etc. And then we have obtained the transfer function of those systems. Now, transfer function is the input output relationship of the system. How we define transfer function? We define transfer function g of s is equal to y of s upon u of s, that is Laplace transform of output upon Laplace transform of input. This is transfer function under zero initial condition. This transfer function we have obtained for various systems when we were dealing with electrical, mechanical or electromechanical systems in the first unit. Now, once we have a transfer function, once we have developed it, now let us analyze our system. Let us analyze this system for the step response. So we will study step response of first order system, step response of first order system and second order system. Right? So this topic we will discuss in this lecture and in our upcoming lectures. So before we begin, we need to understand some terms, and those terms are order of the system, then output, response of the system, poles of the system, zeros of the system. These terms we need to understand before we begin with this topic. So let us see all these terms one by one. Okay. So first of all, order of the system. Order of the system. Now, the order of the system is nothing but the order of equivalent differential equation representing the system. Order of the equivalent differential equation representing the system. Other way this order can be defined as it is the order of the denominator of transfer function after cancellation of common factors in the numerator. Once again, it can be defined as the number of first order differential equations. Number of first order differential equations required for the state space representation. Required for state space representation. So this is nothing but the order of the system. Order of the system is order of equivalent differential equations. Equation representing the system. Or it is also defined as the order of the denominator. Order of the denominator of the transfer function obtained after cancellation of the common factors in the numerator. Also, it is number of the first order differential equations required for state space representation. State space representation. This is called as the order of the system. This is called as the order of the system. Next point is output response of the system. Output response of the system. Now, output response of the system has two components. One is forced response and other is natural response. Forced response and natural response. Forced response is also called as steady state response. Steady state response, and this is called as transient response. Steady state response and transient response. This is also called as particular solution. Particular solution, and this is called as homogeneous solution. Particular solution, homogeneous solution. Right? So this is the output response of the system. Forced response, natural response. That is also called as steady state response, transient response. Particular solution, and this is called as homogeneous solution. Now, what are these solutions that we will see with the help of example? Shortly, we will take one example and I will indicate you what is forced response, what is natural response, what is steady state response, transient response, and all that. Okay. Moving to next point, that is poles and zeros. Poles and zeros. Poles are what? Poles of transfer function are values of S. Values of S. S is Laplace variable that causes transfer function to become infinite. That causes the transfer function to become infinite. And zeros of transfer function are values of S, Laplace variable S, that causes transfer function to become zero. Suppose if I take g of S is equal to S plus 2 divided by S plus 5. if this is the transfer function that I have, s plus 2 divided by s plus 5, then I can indicate this in the s plane. This is called as s plane, and here I'm indicating the real axis j omega, real axis sigma, and imaginary axis j omega. All right. So with this we can plot these values here. Let me indicate this as 1, this as 2, this as 3, this as 4, and this as 5. So here poles are indicated by the crosses and zeros are indicated by zeros. So with this, and these are negative values, let me indicate negative, and let me extend this so that this is -5. So here pole is located at 5. So if I compare this with 0 value, s plus 5 is equal to 0, so it becomes s is equal to -5. So -5. So this is a pole. This is a pole which I can indicate by a cross, whereas 0, s plus 2 is equal to 0, so s is equal to -2. So I must indicate a 0 here. So these are poles and zeros. These are poles and zeros. So pole of a transfer function is a value of s that causes transfer function to become infinite. So if I take s is equal to -5 here, this transfer function will be infinite. And if I take s is equal to -2 here, transfer function will be 0. So poles and zeros are the values of Laplace variable s, causing transfer function to be infinite when it is a pole and causing transfer function to be 0 when it is 0. Right? So this is the concept of poles and zero. Now moving ahead, we will go for understanding the unit step response of the first order system. So this system that we have observed now, g of s is equal to s plus 2 divided by s plus 5. In the denominator, you can see that the order of this equation is 1. Right? So this is first order equation. This is first order equation, or we can call it as first order system, because denominator is having power of s as 1, s raised to 1. That's why first order system. So let us see this unit step response. Unit step response of the system g of s is equal to y of s upon u of s. Y of s is output, u of s is input. Right? So let me write here y of s upon u of s is equal to s plus 2 divided by s plus 5. Let us consider u of s as input, that is unit step. And what is Laplace transform of unit step? Laplace transform of unit step is 1 upon s. So let me write y of s upon u of s is equal to s plus 2 divided by s plus 5. Y of s is equal to s plus 2 divided by s plus 5 into 1 upon s. Now we need to solve this. we need to solve this. I can write a upon s plus b upon s plus 5. A upon s plus b upon s plus 5. So I can write here y of s is equal to, now here we need to understand this is input transfer function. This is input transfer function. This is overall transfer function, but this is input which is applied. So y of s is equal to a in bracket s plus 5 plus bs divided by s in bracket s plus 5. So I need to determine the values of a and b, right? So how I can determine a s plus 5 plus bs is equal to s plus 2. For a, put s is equal to 0, so that this term will be 0, right? This term will be 0. So I will get a is equal to, I will get a is equal to 2 upon 5. And for b, put s is equal to minus 5. So this term will be minus 5. So answer will be b is equal to 3 upon 5. B is equal to 3 upon 5. So overall, what I will get, y of s is equal to, looking at this point, y of s is equal to a upon s. A upon s. What is a? A is 2 by 5 upon s plus b upon s plus 5. B is 3 upon 5 s plus 5. 3 upon 5 s plus 5. So now here, this response that I have got is due to pole in input function, pole in the input function. Here a upon s, 1 upon s, this is because of input. So 2 upon 5 upon s is a pole due to input function, and this is pole due to system transfer function, pole due to system transfer function. So if I take inverse Laplace transform of this y of t, if I want to determine the response, y of t is equal to 2 upon 5 plus 3 upon 5 e raised to minus 5 into t, e raised to minus 5 into t. Now here in this case, this is called as forced response. This is called as natural response. This is also called as steady state response. This is called as transient response, right? So this is called as steady state response. This is called as transient response. Transient response means here there is a term t, where t is changing from 0 to infinity. That's why this total term is changing from 0 to infinity. That's why it is called as transient response. Whereas in this case, there is no term related with the t. So this is going to be a constant term. That's why steady state response. This is steady state response. This is transient response. One more thing is, this is particular solution. This is homogeneous solution. Homogeneous solution means solution which is obtained without input. If I consider only this part, then it is the solution without input. That's why it is called as homogeneous solution. And this is a particular solution which is obtained with the help of input. So I hope this is clear to you. Forced response, natural response, then steady state response and transient response. Steady state response and transient response. Okay. Now here if I take another example, quickly we can take another example of the first order system. I will not go for some values. I will take a upon s plus a. This is a system, a upon s plus a, and this is u of s This is y of s, right? So y of s is again a upon s plus a into 1 upon s. Again, if I take here as a step input, again if I take as a step input, I will get this value. So in that case, I can write a upon s, b upon s plus a. So if I calculate the values of a and b, I can get a is equal to 1 and b is equal to minus 1. So finally, y of s is equal to 1 upon s minus b upon s plus a, not b. This has to be 1 s plus a. So in time domain, y of t is equal to 1 minus e raised to minus at. This is the total response that we have obtained in the earlier example. This is the total response. Y of t is equal to 1 minus e raised to minus at. So this is force response, and this is natural response. Cn and Cf we can write. Force response, natural response, just for understanding. Force response and natural response. So now here, if I take this system and if I plot in the S plane, this is going to be a real axis sigma, this is imaginary axis. Okay, so here I must indicate this as a cross because this is the pole minus a, and this is origin 0. And if I want to plot this response here with respect to time on the x-axis, and here I am having a value y of t, then for different values of t, if I plot t, y of t, so if t is equal to 0, if I put t is equal to here, what I will get? Y of t is equal to e raised to minus at. T is 0, e raised to 0, that will be 1. So 1 minus 1, 0. 1 minus 1 will be 0. Then if I take it is as 1 upon a, if I take t as 1 upon a, what will happen? It will be 1 minus e raised to minus 1. 1 minus e raised to minus 1. This will be 0.63. If I take 2 upon a, it will be 1 minus e raised to minus 2. And you can calculate the value and so on. And similarly, if I take it as infinity, from 0 to infinity, e raised to minus infinity will be, e raised to minus infinity will be 0. So we will get answer as 1. So with this, if I plot it, I can get a graph or curve like this, a response like this. I will get a response like this. This is 1, 0, and like this. So this is unit step response of first order system. This is called as unit step response of first order system. Here we need to note down 3 terms which are very important when we go for time domain specification. That is settling time, we call it as TS. Then time constant, we call it as T, and rise time, we call it as TR. So settling time is time required to reach within the 2% band of final value. That means here it will be 0.98 and here it will be 1.02 maximum value within this range. When you reach within this range, time required to reach within this range is called as settling time. So if I see it here, it is reaching. So this time can be termed as settling time. time required to reach within the 2% band of steady state value. This is called as settling time, TS. Time constant is time required to reach to the 63% of the final value. So this is 63%, 0.63. Time required to reach to the 63% of the final value. This is called as time constant, T. And rise time is, let me write here, 63% of final value. Rise time is time required from 10% to 90% of final value. From 10% to 90%. 10% means somewhere here. 10% means somewhere here. 10% means somewhere here, 0.1, and 90% is somewhere here, right? So this time is called as rise time. This time is called as rise time. So I hope now it is clear to you what is settling time, time constant, and rise time. Okay, so this lecture we have seen various terms: order of the system, response of the system, poles and zeros, and also we have seen how to get the step response of the first order system and what are the various time domain specifications of the first order system, that is settling time, rise time, and time constant. Thank you very much.